Good afternoon, everyone. Welcome to my talk. Today, I will be speaking about the indexing strategy we have built at Trovit in the last few months, which combines a batch indexing layer and a real-time one. All right. So, a little bit about me. My name is Marc Sturlese. I'm a software engineer at Trovit, and I'm basically focused on R&D. And I'm also the responsible for search and scalability in there. Let's see the topics I'm going to cover today in the talk. I'm going to start explaining a little bit what's Trovit, who we are, and what we do. And then I'm gonna continue with the indexing strategy. First, I will cover the batch architecture, which is based on Hadoop and Hive. And then I will go to the near real-time layer, which uses Storm and other related technologies, which I will explain later. Then I'm going to talk about how we mix these both layers together to get the most benefits of each one. And finally, I will speak a little bit about alternatives and future directions. Basically, why we did the decisions that we made, and why we didn't go for other technologies, and which are our plans about adopting new features of Lucene that recently have appeared. Finally, there are going to be a few minutes for questions. So, who we are? What's Trovit? Basically, Trovit is a search engine for classified ads. Our main purpose is to serve good quality results to the end user as faster as possible. We are a tech company located in Barcelona. We started like 6 years ago, more or less. And at that moment, we were present in just the business category and one country, which was Spain and real estate. We were serving query requests for houses, flats, all that stuff. Currently, we are in 39 countries, and mainly in 3 different business categories, which are real estate, second-hand cars, and jobs. And in some countries, we have started working in some other business categories that are deals, vacations, and products. So, this one would be the most common page at Trovit. It's where someone just launches a search request, and we try to give the best results. Here in this ads page, there are 3 different sort of index. We have the organic results, down in the page. Then we have the sponsor ones. And at the top, down of the query, we have some recommendations for the user. I mean, we're going to give to the user related searches about the one that he made. We store these 3 different types of data in 3 different indexes: the organic, the sponsor, and the recommendations. So, knowing that we are in 39 countries, in 3 business categories, 3 different types of index per site, and an average of 4 replicas per index, we have like 1,400 indexes continuously deploying into production. All right, let's go for the batch indexing layer. The batch indexing layer, it's based on Hadoop. I mean, all the documents are crunched by a pipeline of MapReduce jobs. We basically get the data from crawling different websites or XML feeds provided by our sources. And then we just run a sequence of MapReduce jobs and finally build the Solr indexes and deploy them into production. It's important to remark that we use Hive to get stats of each of these MapReduce jobs. I mean, in Hadoop, as we are dealing with sequence files and binary data, you cannot query anything or do seeks to see what's happening. So it's good to have Hive to get reports of each of the MapReduce jobs. Here we can see an overview of the batch pipeline. As I said before, we are getting data with getting incoming data from crawling websites and XML feeds. And basically, we can see the sequence of MapReduce jobs here. First one would be the ad processor, which takes care, for example, of filter low-quality ads or apply business rules to all the documents. Then we have a matching phase, for example, that it's to classify and properly identify our data. To do that, we use external data sources. For example, this would be like loading a geolocalization table and then try to match all the documents with it. Then we have another phase for expiration, like to discard 2 old documents, the duplication, that just computes and filters duplicates. And finally, there's the indexing phase. In this one, we build the indexes in HDFS, then download to local, and spread them to the Solr replicas. For doing this deployment, we use multicast, because it's really fast. I mean, if your bandwidth is good, you can send all the indexes at the same time to all replicas, but you have to be careful with that as well. You have to keep it really under control, otherwise you can just start sending packets of bytes to all the data, all the nodes in your network, and you can crash your website or even your phone line if you're not careful. As we can see, we are saving Hive stats in each of the phases. So the good things of this batch layer is that index is always been from scratch. This means that we have a small number of big segments in the index. I mean, as we are building the indexes with Hadoop, you just can end up with a single segment. And this is really good for search query response time. I mean, the more segments we get, the more the query response time decreases performance. So building the indexes this way, we can have a single segment or just a few segments per index. Then with the multicast deployment, it allows us to send the indexes to all the slaves at the same time. And well, basically, HDFS is really good for backups. I mean, as you may know, HDFS have replication 3 by default. It means that we store backups of the indexes there, and if a node goes down or a couple of them goes down, we're sure that we're not going to lose our data. That's good. I mean, having indexes with a single segment is fast and really good for performance. But the main problem is that this approach is not even close to real time. I mean, crunch documents in batch means to wait until all is proceed, and this can take a few hours. I mean, since we get the data, the input data from the feeds and the crawled sources, till everything is indexed, it might, I don't know, it can take like 5 hours, 4 or 5 hours. And you know that during this time, you're not going to get fresher results to the user. And we really don't want that. What we want is actually to show the user as fresh results as we can. So here's when Storm comes to the rescue. Storm allows events to occur in real time. How many of you know or have worked with Storm? All right, a few. So I'm just going to give a very brief explanation of how it works, and then I'm going to explain how we're using it at Trovit. Well, Storm, it's a distributed real-time computation system. It said that it's something really similar to Hadoop, but with no latency, working in real time. This means that it shares many properties in common, like it has fault tolerance, horizontal scalability, and reliability. With horizontal scalability, as you may know, if you are being slow processing the data, or you want to process more data in the same time, you just have to throw more machines to the cluster, and everything's going to be faster. And the main difference with Hadoop is that, of course, it's real time, and it has really low latency. OK, this is how we are using Storm at Trovit. First, let me explain a little bit about the basic concepts of Storm. In Storm, you must know what's a tuple, a spout, a vault, and a topology, basically. A tuple, it's like the minimum working unit that you have in Storm. It's like a document in Solr, more or less. Then you have spouts and bolts. The spouts are the sources of these tuples. I mean, a spout just connects to a database or an external data source, as can be a Kafka queue, another sort of queue, or even plain files, wherever you want to use. And they just start fetching data and throwing it to the cluster. Then we have the bolts that just receive tuples and do the proper processing. They can work as filtering or do whatever computation you want. And once you're done, you can emit the tuples to another bolt, or you just can store the results in whatever storage system you have, like MySQL or NoSQL database. Even you can keep in memory, or in this case, store results in Solr indexes. What is called a Storm topology, actually, it's like an acyclic graph of spouts and bolts. Basically, here, this graph is pretty simple because we just have 3 layers. And let's see more or less how they work. As I said before, and same as in the batch pipeline, we have the source of data, which are XML files and Kafka partitions. Then we have 2 different sorts of spouts. There are the ones that read from Kafka and the one that reads these XML files. They just keep getting the new documents from this data, from these sources, and then sending them to the document manager vault. The document manager vault, I would say it's like a simplified version of the Hadoop pipeline. I mean, it takes care of like applying business rules, discarding low quality documents, do the matching I explained before, like for doing geolocalization or categorization of the jobs document, expiring low quality ads, all this sort of stuff. And then it sends the documents to the indexer vault. And the indexer vault, what basically does is just add the documents to all the Solr replicas. I mean, the indexer vault, if it receives the document, for example, of real estate UK, it knows that index in which replicas of the Solr cluster is, and it's just going to send that document to all of that replicas. Another thing to remark here is that you may see here that I write how we distribute the data from one spout to another vault and from one vault to the other. Basically, we're using shuffle grouping from the Kafka spout to the document manager vault. This means that this would be like threads. I mean, this would be the document manager vault using 3 threads. Using shuffle grouping, we are saying that we really don't care each document to which of the threads is going to go. I mean, all are doing exactly the same job, so we don't care where it goes. In the indexer vault, we are using field grouping. And I'm going to come back here later to explain exactly what does it mean and why we use that. As far as we have seen, in the Storm topology here at Trovit, the spouts just read and send. The document manager vault processes documents and classifies. The indexer vault adds documents to Solr. And well, you might imagine here, like there's lots of logic replicated in the batch pipeline and in the Storm topology, as for example, the geolocalization, as I said, or the job category classification. This was a big challenge because there's replicated logic, but the implementation is completely different. For example, for doing geolocalization with Hadoop, we are using like reduced size join fashion, where we get in one side the documents and the other the geolocalization data and try to match it. And well, with Storm, it's totally different approach. I mean, we just load in memory or in a storage all the different geolocalization data that we have, and try to do lookups from the documents and try to match this data. So, with all this system, I mean, we are able to index data in near real time with low latency. So basically, let's index it all the documents that we have. Let's put it into Storm, and wow, index everything. But there are some dark sides here, because we can break our own house here. I mean, we had an X number of Solr replicas or Solr slave that were handling X traffic of search query requests. And suddenly, we just start launching hundreds or thousands of HTTP requests from Storm to add documents. And this really can overload Tomcat, overload your Solr cores, and even bring down the servers. So there are some points to take into account here. Some of the things that we do to solve this problem, to try to overload the servers. The first one was to do field grouping on the indexer vault for politeness reasons. What we do is we send all the documents from the same business category and country, which means to the ones that exactly in the same index, to just one thread of the vault. This way, we are sure that at the same index, we have just one thread sending documents to them. So it's very easy to control politeness here. And if we see that with a thread, it's all right, and we can even handle more traffic with no problem, we just can change the field grouping and start sending the documents from real estate UK to 2 of the threads. So we are going to have here double throughput. And we can keep doing this till we have the desired load, but not overloading things. More things that we can do to increase performance here is like small bulks to reduce insert request. I mean, in the beginning, what we were doing is just sending an HTTP request per document, but it was like producing lots of overhead, and we were doing like so many queries to Solr that were totally unnecessary. What we end up doing was like each indexer vault has a buffer, and we just keep storing the documents in the buffer. And we just send an HTTP request to Solr every 30 seconds or something like that. So this really decreases the load and make things much faster. Another thing that we have to deal with is that we might be committing on many cores that exist in the same host, in the same slave. And the commit might occur in exactly at the same moment of time. And this can be painful. Let's see it with an example. Imagine this is a scenario. We have here 2 different indexer vaults, the one of cars US and the one of jobs for Brazil. And here we have all the Solr replicas cluster. We have the slave 1, 2, till n, all right? Imagine the case when the indexer vault from cars US and the one from jobs BR decide to commit exactly at the same point of time. Well, they are sharing this slave 2 replica, all right? So 2 commits might occur in the same core at exactly at the same moment. And having just 2 cores, it's not a problem. But or Solr slave, some of them are handling like 20 cores or more, and we don't have enough RAM to store the documents in memory. So if you hit 20 commits exactly at the same point in the same replica, you're going to suffer a little bit. So what we do here was just to add a Zookeeper layer. And when an indexer vault wants to commit in a server, he asks Zookeeper if someone else is committing. If no one else is committing, he just can commit and then leave. But if someone else is committing, Zookeeper is going to tell you to wait till the commit is done. Then it's going to give you the token. You can commit, give back the token to Zookeeper, and that's it. Doing that, basically, we cannot commit exactly at the requested point of time. But the good thing is that we are not overloading the server with too many commits. With this near real-time layer, what we actually have achieved is that now adding documents is fast. We keep the number of segments in the index small, and we also are avoiding merges on big segments. All right, this is because we are just adding documents in this near real-time fashion during a period of 4 or 5 hours, for example. This time we keep adding new segments with the new documents, and these segments are gonna keep merging with each other. But as we know, in 3 or 4 hours, the new batch index will come with and we are gonna stay again with just one single segment. So the good thing here is that our number of segments, it's always small, and we are just merging the segments with each one with a small one, but never touching the big one. And well, we are just adding new documents. We are not doing deletes or updates. And basically the reason is the same, because we want to stay away of touching the big segment. So just adding new documents, we are sure that we are always creating new small segments and not merging with the big one. Putting everything together, this would be an overview of the mixed architecture. As I said before, we have the Kafka partitions and XML files as input sources. And we have the two layers running in parallel. In the top, we can see the sequence of MapReduce jobs. And here in the bottom, the storm topology. I said before that with the storm topology, we are just adding the new documents. But you may think, all right, if you are just processing XML feeds and not comparing with any past iteration, how do we know which are the new documents and which not? So having the batch pipeline, it's easy, because there's one of the MapReduce jobs before the pipeline finishes that we already know which are the documents that are going to be indexed. So what we do is we can just dump all the IDs of the documents that are going to be indexed in this case in a HBase table. So we can store all the IDs and some extra metadata that we might need. And then in the storm topology, for each document that we get, we just have to query to the HBase table and see if it contains the document or not. So if it's not contained, we know that the document is new, so we can process to add it to the index. Finally, here we can see the last Zookeeper layer. And this is the main reason for this is that because when you have to deploy the new index and you have been indexing near real-time documents in the production one, you may have some issues. We have here a locking to control these issues. So the thing is, when swapping indexes, some near real-time documents might not be contained in the new batch index. And this can lead to inconsistency. What does it mean? Well, with the near real-time layer, we may add a new document 30 seconds ago, and then we deploy the new batch index. But the input of this new batch index was older than this document indexed 30 seconds ago. So the document would just disappear. And not because it's low quality, and not because it has expired. It's just because we just did a time jump to the past. We had a new document, and now it just suddenly disappeared. We really want to avoid this issue, or call it wherever. What we do here, I'm going to explain it like with a picture, because I think it's going to be much easier to understand. We just have regular pipeline, XML files, run the jobs, deploy the slave. Here the green line means batch indexing, and the yellow one that's going to appear, it's near real-time layer. So nothing special here. We just deploy an index. Now, another set of XML feeds comes to production, to HDFS, and to Kafka and everywhere. So we just launch another batch pipeline. And at that point, we launch the near real-time layer. So it starts getting the same input as the batch pipeline and start adding new documents to the production slave. Till here, everything's all right. I mean, when we finish deploying this index, we're going to have all these documents as well. So everything's cool. But what happened if we just imagine there were just a few new documents in this set of XML files? We process all of them, and then we receive another set of XML files. At that point, the near real-time layer is going to start indexing the documents to the slave. And here is the problem, because this pipeline is not going to have these documents. Here is when the time jump would happen. Well, this can be easy fixed. What we do is when we index documents in near real time, we don't just add them to the Solr index. we add them to another temporary storage layer. In this case, it's HBase. And so when this pipeline finishes, we just have to scan the HBase table, querying for from different time ranges, and we just can get the documents that are not contained in this index. So we just can index them and deploy the new index. We will be sure that we are totally in synchronization with the index that was previously into production. As we have seen, if we want to avoid troubles when swapping the indexes, the near real-time documents must be stored in a temporary storage. And then we have to fetch these documents from the storage and add them before deploying the new index. With this, well, doing that, we just avoid these time jumps. All right, so the advantages of this mixed architecture basically is that we have near real-time inserts with low latency. We just let Hadoop handles the deletes and updates. I mean, we have no rush for those. Of course, we have to expire the old documents and modify the ones that have modifications. But it's not, I mean, if we wait for 3 or 4 hours for that, it's not a problem for us. The thing is just to always be showing to the end user fresher results. So it's why we just insert documents with the batch layer, with the near real-time layer, sorry. Then, as I said, we have no merges on big segments, so the query response times are going to be optimal. As I said before, the big segment, it's never touched. We just experience merges of small segments, and every 4 or 5 hours, we're going to get a new index with just one segment, so no problems on having merges of 2 gigabyte segment, for example, or stuff like that. That when that happens, you may suffer of performance in query response time. Well, the system is tolerant to human errors as well. This means that if we introduce a bug in the system, even in the near real-time layer or the batch one, we just have to fix the bug and then run again the batch layer. As the batch layer always reprocesses all the data, we are sure that all the documents would be properly computed and we'll leave all the data with no bugs. If we don't have the batch layer here, imagine the problem when you introduce a bug in a delta indexing strategy. When you fix the bug, all the new documents are going to be all right, but the ones that you have already processed that are buggy, maybe it's difficult to be able to fetch them again and reprocess. And having the batch layer ensures us that if we fix the bug, everything's going to stay all right. And then another thing that the system lacks a little bit is that we may have temporary loss of accuracy on the near real-time layer. For example, the most clear example is duplicate computation. In the batch layer with Hadoop, Hadoop has lots of powers for duplicate computation. I mean, we can do some clustering of the documents, group them, and then for each group, iterate over all the documents of a group and compute the Levenstein distance or wherever the algorithm for duplication we have, and be pretty accurate on which are the duplicates on our data set. Currently with Storm, we cannot do that at all. I mean, we can handle duplicates in a MD5 hash fashion, but it's much less accurate. The good thing is that we know that in 4 or 5 hours, the index will be again built from scratch with all the duplicates properly computed with Hadoop. Well, Solr Cloud, why not? I mean, it's totally for real time. Basically, we were looking at it like a few months ago when we started building this architecture. And well, basically, the problem is it was pretty alpha at that point. Now maybe works good, works all right for the vast majority of use cases. But the thing that we didn't want of it is that it's totally incremental, insert, update, and deletes oriented. This means that you pay segment merges per real time. I mean, in Solr Cloud, you are just always doing incremental indexing so you never index. And if you want to optimize the index, or at some point you're going to hit a merge of 2 big segments, and then at that moment the query response time are going to be irregular. Another thing is that we really need to deploy the full indexes fast. And currently with Solr Cloud, if you want to deploy a whole index, you have to use the rsync or HTTP replication, I think, which go first to one replica, then to the other, then to the other. And if the indexes are big, it's going to take a while. And even if you can deploy it, you will be able to deploy it to a new core, but not to the production one. Now, this is, I think, the stuff of deploying a whole index into production using Solr Cloud. It's much easier due to the collection aliases feature, because I think you can deploy a brand new index to another core, and then using the aliases, you can tell Solr that the new core is the one that is the production one, and automatically all the queries are going to start going to the new index. And well, thinking in futures lines, basically we want to introduce the Lucene real-time feature. This basically allows to see documents in the index before they are commit. It's an interesting feature for us to have, but it's really not a must. I mean, it's not like our users can introduce documents and at the same time like pushing Command R and see if the document has been already indexed. Or documents are coming from XML files, which may change, I don't know. It depends on the source, but maybe 2 times per day, maybe 10 times. But it's not like a matter of seconds. And well, the good thing is that I think it's going to be easy to integrate that in the current architecture. I mean, for example, Solr Cloud really supports the real-time feature. And the problem of this feature is that you just add a document and it's kept in memory. So if the server goes down, you might lose that data. What Solr Cloud does, I think, is it just had a write log ahead in each of the slave. So every time a document is stored in the index, it's stored as well in this write log ahead file. And if something goes down, when you turn up the server, it's going to read this write log ahead file and index the documents again. Not exactly sure if it's like that, but I think it's sort of this. In our use case, as our near real-time documents are always stored in an external data source, in its case an HBase table, if we go down, we can easily just turn up the server and scan the table and add all the documents again. I think basically that's it. Questions? Oh yeah, what's the multicast deployment? And well, where I said it's like a protocol where you just send and all the replicas receive at the same time the byte. So all the replicas are able to get the index at the same time. As I said, it's a bit dangerous because you have to control your network, because you might start sending the index not just to the slave replicas, but to all the hosts on your network. And that's because I said you have to be pretty careful about that. Well, when I say low quality ads, I mean, it's like we have like simplifying it. It would be like we have a set of business rules, like if the content is too short, or if it contains like stop words or stuff like that, or the document says that it has a city and that city doesn't belong to the country we are dealing with. I mean, it's just a set of rules.